Hello, in this video lesson, I will give you information about dimensional tolerances. In general, we consider tolerances in mechanical engineering under two different topics. The first one is dimensional tolerances. The second one is geometric tolerances. In order to ensure the assembly, function and interchangeability of a part we design or manufacture, it must first be within the boundary of a dimensional accuracy and then the geometric accuracy. We call this limit definition a tolerance. There are maximum and minimum points for this limit. In order to ensure the compatibility of the parts, it must first be dimensionally compatible. For example, if we consider the mounting of the shaft and a plate with a hole mounting, firstly, there should be a dimensional compatibility between the dimensions of the parts. This compatibility is called over the nominal diameter. A connection without nominal diameter AAULT is not possible. The main condition that we should consider as a dimensional tolerance is the function of the connection for us. We consider this functionality under three main topics. A connection can be defined as a clearance fit connection for easy assembly, or it can be defined as a sticky fit which is called transition fit. Finally, the parts can be defined as interference into each other which is interference fit. We will talk about this in detail later. Tolerance between parts should be applied after the decision has been made based on the functionality. We determine the dimensional tolerance of parts with the maximum and minimum dimensions of the nominal size. The tolerance of a measure is the measure between the maximum and minimum limits of the part. For example, if the nominal size of our part is 25 mm, if the maximum size of our part is 25.5 mm, and the minimum size is 24.95 mm, our tolerance between the maximum size and the minimum size is 0.1 mm. In the technical part drawings, we show the tolerance of a dimension with plus and minus signs or dimensions with a letter and a number in the figure. You can see the direct measurement limits in this example. The tolerance display is in plus and minus representation. If our part has no significant dimensions to be specified, we can also define the general tolerance to our part. This general tolerance can be shown in the title block, or as a note somewhere in the drawing. In plus and minus tolerances dimensions we also have a chance to define our tolerances differently. We have two types. The first one is unilateral. Unilateral means when the tolerance applies in only one direction so that one value is 0. The second one is bilateral when the same or different values are added and subtracted to the nominal dimensions are defined. As we give the tolerances to linear dimensions we can also define tolerances to the angular dimensions. You can see the example in the figure. Here I want to explain which conditions we should have to think when we define the dimensional tolerances. You can find this example in the lecture notes. The part's nominal length is 70 mm. The length has maximum of 70.3 mm to a minimum of 69.7 mm. There are 29.8 minimum and 30.2 maximum dimensions for the step on the top. 2 states and for the 30 mm nominal size. If we summarize the solution in a table, size of has 4 different possibilities. I would like to give another example. In this example, when we define the dimensional tolerance, we need to think about certain possibilities and reduce the apparent probabilities to a couple which is maximum and minimum values for the A dimension. For this, we need to give our measurements with a certain systematic. The part shown in the figure, there are 3 possibilities, with 2 limits which results 8 possibilities for dimension 8. In order to reduce this possibilities we must define the dimensions to a reference point for a surface. This condition is called tolerance stack up, and this stack up condition must be avoided. If a single measurement is given from the left side of part for the whole axis dimension at the far end, whole axis size will have only 2 dimensions, with the options 1 maximum and 1 minimum. At this point I would like to define about 2 terms. The first one is maximum material condition and the other one is the least material, the condition of part when it contains greatest amount of material. Maximum material condition of external feature, such as shaft, is upper limit, while of an internal feature like hole is lower limit. The condition of part when it contains least amount of material. Least material condition of external feature, such as shaft, is lower limit, while of an internal feature like hole is upper limit. When determining the tolerances for the parts, the function of a part is important. We consider this function under three main topics. A connection can be defined as a clearance fit connection for easy assembly, or it can be defined as a sticky fit, which is called transition fit. Finally, the parts can be defined as interference into each other, which is interference fit. The loosest fit, or maximum clearance, occurs when the smallest internal part shaft is in the largest external part hole. The tightest fit, or minimum clearance, occurs when the largest shaft is in the smallest hole. We determine the tolerances by using international standards according to the functionality of the parts. In Turkey we use our ISO 286-1 and 2. We show the tolerances of a dimension in different ways in technical drawings, with plus and minus signs or with the representations which are defined in the international standards. From the standards example for a H8, F7 connection with a nominal size of 40 mm hole, the maximum dimension of the hole is 40.039 mm, and a minimum dimension of the hole is 40 mm, which is expressed simply by 40H8. Here 40 indicates the nominal size, H indicates the variation of the tolerance, 8 indicates ID dimension which is defined in ISO 286. And the capital H in this representation, it means that it is a hole size. If the letter is small in dimension tolerance representation, it is a shaft size. For the shaft with 40 mm in this connection, the maximum size is 39.975 mm and a minimum size is 39.95 mm. IT grades specified in ISO 286-1. Here, each IT grade specifies a measurement in micron for a size range. For example, for IT grade 7 for the size 40 F7 in the previous example, as seen in the table, the ID7 between 30 and 50 mm is 25 micron. In the previous example, we can calculate the minimum and the maximum shaft dimensions by using the IT grade value. The maximum size can be evaluated by the subtraction of the IT grade from the nominal size. This operation 40 mm minus 25 will result 39.975 mm. For the minimum size of the shaft we will again subtract the IT grade value from the maximum shaft dimension. This operation will give us the result 39.95 mm. Now we will explain the change of tolerance with a graph. First, let's consider a plate with a hole with nominal size. Let's draw a line from the 0 point on the nominal size of the hole in this plate. There are 3 states around the 0 point. For the H tolerance case in our example, we need to think that the hole size has grown because it is above the line. Starting with the letter H, we can say that the hole gets enlarged of JS around the 0 point. In other words, plus minus tolerance state. From J to Z, we can think of the tight tolerance situation in which the hole size is getting smaller. Similarly, we can think this situation for a shaft where the shaft size shrinks from the small letter H to a letter. The symmetrical dimension tolerance state is K, and the shaft size from the end letter gets larger towards Z, which will result in a tight connection. In this slide you see the tolerance relationships between parts. In the figure, there are 2 basic tolerance model which are hole basis and shaft basis. We also have 3 option connection which is previously mentioned. Those are clearance fit, transition fit and interference fit connections. The hole basis system is shown on the left column and the shaft basis system is shown on the right column. We will explain how we are going to select the basis according to application through examples. In this table, the loosest fit is on the top side and the tightest fit is on the bottom side. In the table, first 3 rows are used for clearance fit connections. The 3 rows in the middle are used for transition fit tolerances. The 3 rows at the bottom are used for interference fit tolerances. We will give example solutions table for all these 3 connections. Let's calculate a hole and a shaft dimension for a nominal dimension 35 mm with tolerances H7 and G6 respectively. The hole dimension with a tolerance of 35 mm H7, we calculate the maximum and minimum dimensions by using the tolerances given table. You can find the table in the submission. The table consists of 2 sections. The top section is hole basis. The bottom section is shaft basis. For the hole size we will look at the top of the table. We will search and find tolerance letter in the table. Then we search our dimension range. In our case it is between 30 and 50 mm as we will combine the IT grade given in the example. And we will combine these inputs on the table. The maximum tolerance in this table is given with ES. And a minimum tolerance in this table is given E. Let's continue with the numerical values. For the hole dimension 35 mm H7, we will combine the letter then the IT grade, with the dimension range. For maximum dimension the S is plus 25 microns and a minimum dimension A is 0 micron. After finding the values of maximum and a minimum tolerances, we create a simple table to calculate the maximum and a minimum dimensions by adding the tolerances to the nominal value. Here, all our values are positive. The maximum size for the hole is 35.025 and a minimum size is 35 mm when we add the tolerance values to the nominal dimension. Similarly, for the shaft dimensions, for 35 mm G6, we take the tolerance deviation G and IT grade 6, we combine this column with the 30 and 50 mm rows. From the table we find the maximum value ES minus -9 microns and minus -25 microns for the smallest dimension. We again put these values to the table and make the summation operation of these values to the nominal dimension. For this shaft tolerance bar both tolerance value is negative. And for this reason our maximum and minimum dimension will be below our nominal diameter. You can see the summation results. The maximum dimension is 34.981 mm and a minimum dimension is 34.975 mm. If we examine the tightness situation in the assembly, if we subtract the maximum hole from the minimum shaft dimension we will have 50 microns allowance for maximum tightness. This case is the loosest case in our connection. If we subtract the minimum hole dimension from the maximum shaft dimension this is the tightest case which is 9 microns. Here all our values are positive. And we can call this connection clearance fit. The question comes to our mind is, what happens if we choose H11 tolerance instead of H7? In this case, we actually increase the tolerance value. If we have a larger hole we increase the size of the hole. Let's analyze the tolerance value with H11 hole value. The maximum for the H11 in the table is plus 160 microns. The minimum size is again 0 microns for H11. Increasing the IT grade is a bad choice if we want a tight connection, but a good choice for easy manufacturing. If you want a good quality please keep the IT grade small. Let us now consider other situations. More tighter tolerance states. As an example, we will investigate the transition fit connection in the table, then 7H6 for nominal size 125 mm in shaft basis system. Then 7 for 125 mm. For hole dimension from the table, the maximum dimension is -12 microns and a minimum dimension A is -52 microns. For shaft size 125H6 size, the largest size is 0 microns and the smallest size is -25 microns. If we put the values into a table, for maximum tightness is -52, and a minimum tightness will be +13 microns. We have created a connection where the largest tightness is -52 microns and the smallest tightness is 13 microns. There are 2 possibilities here. The connection we created may have 13 microns cavity, or it could be a tight connection with -52 microns. As you see our solution this time it is not a loose solution. Let's make another application for a tight connection. Let's examine the H7S6 connection for the 50 mm hole basis system which is near the limit in the table. Since 50 mm is the nominal size, we use the tolerance values in the row between 50 and 80 mm, not the row of 30 to 50 mm. For the hole size is 50 H7, 30 micron for the largest size, 0 micron for the smallest size. For the shaft, 50 S6, maximum dimension is ES plus 72 microns. The minimum dimension AE will be plus 53 microns. If we create the table, and make the necessary calculations, both tightness are negative. We generate a tight connection. In the examples given, we used different tolerance systems, hole basis or shaft basis. So how do we decide the system basis? There are two situations, but we first look for what is the type of the common part, or the cost of which part is critical to us. In the first case, we have to question whether the common part in the connection is a shaft or a hole. For example, let's consider two different tolerances for the bush and body working in a tailstock body. We want the bush to move slightly within the body part, but within a reasonably tight tolerance, shortly transition fit. For such a connection is H7, H6, or H7, K6 for the tightest H7, then 6 tolerances for a hole basis system. Or are we going to choose from H7, H6, K7, H6 and N7, H6 uniform shaft basis tolerances? At this point we will look at the importance of other connections, using the same connection items, like the flange on the back side. Flange connection is not very important to us. The connection between the flange and the body does not affect the function of the flange. For this reason, the common part concept is not very important to us at this stage. However, in this example, it is difficult to manufacture the body part and it is costly to scrap it due to an error in its manufacture. In this case, choosing the body part larger in tolerance value will avoid scrap ratio. For this reason we will install the system on the big part. If we want a tight connection we will choose H7/N6. If we want loose connection H7/H6. Let's give another example about tolerance. We will examine the tolerance between a sliding door wheel, the connecting pin, bush and the wheel connecting bracket. Here, the wheel number 2 and the bush number 3 are connected by a tight fit and turn together. The connection between pin 4 and collar 3 is clearance fit condition which allows the wheel to turn. Our common part is the number 3 bush in this assembly. However, it has to have two different tolerances in terms of functionality. In the bush pin connection, the inner diameter of the bush and pin can be clearance fit tolerance of H7/G6 or G7/H6. The outer diameter of the same bush is connected to the wheel by a tight fit connection. In the connection here, the bush shaft will be considered as a shaft. In this connection, the tight fit tolerances H7/P6 or P7/H6 tight fit tolerances can be considered. Here, one of the tolerance pairs H7 or P7 for the wheel and one of the P6 or H6 tolerance pairs must be defined for the ring outer diameter. Another case from the previous exams, the tolerance is determined according to the type of the common part. In the example, the tolerance between the body number 1 and tool holder plate number 2 connected by pin number 3 will be examined. There is no step on the pin. When we look, the function of pin number 3 is fixed to the body number 1, but holds the tool body without preventing the rotation of the tool holder number 2. Here tight connection between pin and body, there is a need for a mobile connection with a pin. Note that the pin is common in both connections. When the dimension is defined in any tolerance basis, other connection dimensions can be adjusted according to the function. If the common pin is considered as a shaft, some tolerances in the shaft basis system are considered. For example, After determining the size between the pin and the body part number 1, we can choose interference fit, let's say S7/H6, this time pin has H6 shaft for the pin. For this reason we choose the same pin tolerance H6, and the body tolerance S7. And for the tool holder with G7 for tool holder. See you in next class.